Okay, let's go ahead and get started here. First and foremost, welcome to Autodesk Virtual Academy, brought to you by your friends here at KETIV Technologies. My name is Nigel Umbayek, one of the customer success managers here on the team, and your host for today's and just about every other day's AVAs. So certainly welcome to everyone who's joined the webinar today. I'd like to introduce my colleague here, Jeremy Gerdes. Jeremy, how's it going?
Oh, it's going pretty good. How about yourself?
I'm doing well. Doing well. Thanks for asking. Jeremy is one
Awesome.
of the AEs here on the team, and he works primarily on our Lifeline support team. So odds are, if you've called into our Lifeline before, you might have received some assistance from Jeremy here. But Jeremy, additionally, too, is one of the experts here on the KETIV team in regards to things within the Inventor Design Accelerator, specifically a lot of the power transmission. That just happens to be where he's from in industry, and so it makes sense for Jeremy to kind of be the in-house expert on those things. Which is why Jeremy's going to be going over today's presentation about synchronous belts. I know last time Jeremy was on, we did some gear and pulley stuff, and today we're just going to move on to another thing with the belts. So without further ado, I think I'll just pass it on to Jeremy, and we'll go ahead and get started. Do you have anything else to add, Jeremy, before you jump in?
No, I think that's pretty much it. Just going to go over the synchronous belts and see how they work and get going on that.
Sweet. So what we're going to do here is we're going to go ahead and get started with the presentation. Um, I know that there's a poll question we'll bring up as well. So Jeremy, just let me know when you want me to fire that. And additionally, on top of that as well, if you have any questions, go ahead and type those into the panel at any time, and we'll go ahead and address those. So go ahead and take it over, Jeremy.
All right, thank you. All right, so today we're going to talk about the synchronous belts in the Design Accelerator and Inventor. So a little bit about myself. I'm an application engineer with KETIV. I've been in design and manufacturing engineering for over 12 years, been using Inventor for the same, and I came from designing industrial pressure washers and accessories with doing power transmissions for over 8 years. So you may ask yourself, what are design accelerators, or what are the synchronous belts in the design accelerators? Well, the design accelerators, simply put, help you with problems of calculations and parts that are already built into Inventor. Let Inventor do some of the math and work for you. And they have tons of different options and different design accelerators in there. They have fasteners, frame generator, power transmission, springs. The synchronous belts, you can do drive creation for validation and optimize the layout of the pulleys for the RPMs and outputs and power transmission that you need. There's a few different ways to do it. You can generate the belt drives with using pulleys that are from your parts that you've drawn in Inventor, or you can use pulleys that are built into Inventor with their calculations. And when I talk about the design accelerator, you have to be in an assembly to access it. So you have bolted connections up here, you have pins, you have frame generator, frame analysis, shaft, gears, bearings, belts. There's V-belts, synchronous belts, and chain drives. You can do keyways. There's disc cams, splines, O-rings, compression, and different springs. So one of the simplest and first ways to use the design accelerator for the synchronous belts is if you already have pulleys in your library of parts you've done, and you have legacy design data of, I know at this distance and this distance, I need this belt, and I know it's going to work. We've already built models that are similar to this. We've built these distances in other applications with this horsepower and these RPMs. So we already have the data, but we just want to show the belt. And then you may ask, well, why do we even need to go down that road? And I'll tell you this from horrible experience. We had a project many years ago and one of the guys that was doing it was doing the gearing. One of the other gentlemen was doing some of the pressure hoses, and there was a lack of communication and lack of space when they both took up the same spot. So having some of those representations in the model helps alleviate the issue of, well, where am I going to run this hose now, or this belt guard? So let's go over how to do that. All right, so we have a pretty basic model here. We have a 10 horsepower motor and a high pressure pump. And these are pulleys that I already have in my library. So when you go into your design accelerator, you have to be in an assembly. So we start off in an assembly, already have it. Then we click on the design tab. And again, we have, fasteners, frame generators, but we're going to be dealing primarily with the power transmission for today. So up here, you have your V-belts, synchronous belts, and roller chains. So we're going to be dealing with synchronous belts. Click that. And then you get this component generator that pops up. And at the very top, you'll have all the different belts that are built into the system for the synchronous belts. You have double-sided, you have single-sided, double-sided, symmetrical, staggered tooth. But for this instance, we're just going to use an H synchronous belt. So the first thing that you need to do is select the mid plane for the belt. And the first pulley that you're going to deal with is the driven pulley. It is the powered pulley. So then coming down the generator, you have the plane offset. And what that's meaning is from here to here, where is it going to place it? And since I already know that in this H belt, I use an 1.5 inch width belt, put that there. Then we get down to the pulleys themselves. There's a few different options. Since we're going to be using existing pulleys, I'm going to click the existing. Then I'm going to select the pulley. And as you come over here, you'll get more properties that you can adjust. But when you're using the component or the existing components, you can't do that. We'll deal with that in the next. So again, we're going to go to the pump pulley, click existing. And you can see how this line here is red. It means that the software itself knows that there is no adjustment built in. The pulleys can't adjust for tension. But if I already have a tensioning mechanism in place, or I already know how I'm going to do it, it's okay. This is more or less just for representation for clearance issues that we're going to do. So then I'll go to OK. And it's going to give me some warnings because I'm not following the built-in rules. And in this instance, it is okay. Hit accept. And now it throws a belt on there. And now I know that, if I look here, well, that's pretty close. Maybe I need to shift or adjust the way that I'm going to mount this to move this cross member out of the way. So that's one reason why you would use it, even if you're just using parts out of your own system. So let's. So then here's the biggest help for it is using the pulleys and the calculations that are built into Inventor. Why would you use this method? This method will let you to figure out where to place your components as a whole. It'll tell you the proper length of belt, and it'll tell you the proper pulleys to be using with calculations and rules that are based off of the ISO, DIN, and ANSI standards. So for this first example, same components, but if we've never built this before and I don't know where I need to have my pump placed for a correct belt length, using standard components instead of ordering custom belts or custom pulleys to fit. So I'll come back to my design accelerator, Synchronous-Belts. Again, we're going to use the H belt. I'm going to choose my mid plane. And so for this first one, we're going to make sure it's a component. And then here's the placements for these. Since we're not using an existing, we have to figure out where exactly it's placed. You can do fixed by coordinates, fixed position by selected geometry, free sliding position, direction driven, and then rotational driven. Since I know that the motor is not going to move, I'm going to place it on that shaft. I'm going to pick fixed position by selected geometry. Then I'm going to come over to here, the three little dots, and this will let me change the pulley properties. I can do a custom size if we order a custom made pulley, but I'm going to use a out of the box, off the shelf component so I can appease, purchasing. And I've already ran what the RPM requirements and ratio needs to be. So I know for this it needs to be a 28 tooth pulley. But if you change it or want something else, you can type it in, or you can go to the values here. And these are all the pulleys that are built into the system. So they have quite a few. So, okay there. And now we're going to go to the next, to the driven pulley. Again, it's going to be a component because we're going to be making it now. But this one, since I need to know, or I want to figure out where I need my pump to start for the tension for a belt length, I'm going to do the direction driven by the sliding position. So if I know I plan to tension this belt by pulling the pump up or down, I'm going to use a vertical plane here. Come over to the properties again. And I know my ratio needs to be around 1.48 for the pressure and flow out of the pump for the RPMs. So I know already it's a 40-tooth pulley. And in this box, the number of teeth, I can now change how long the belt is. So if I have 120, slides it up. We'll go back with a 108, 114. And you can see now that this line is green because in the system, it realizes that there's tension. You're able to slide the pulley. Then next to the design tab, you have your calculation tab. This will let you enter the information in to figure out if the belts are going to be the proper width, if you need to put a longer belt, a shorter belt, if the pulleys need to adjust for what built-in calculations are going to be. So the first parts are going to be the power. It's a 10 horsepower motor. You need to enter the RPMs, service factor, and the efficiency. And the efficiency is a big thing in a correlation to the belts and proper alignment, because if you're able to get the proper tension and alignment on the belts, the efficiency goes up, and we all want that. So we can, after entering the information in, calculate, and it tells me that the design is in compliance. So I'll come back here and go, okay. and no warnings this time. So I go, okay, now that's where my pulley is going to be for this. And I can move my pump up. So I now know that this is the height in which my pump needs to be at for the proper tensioning for that efficiency gain. So then there's also with the synchronous belts, you can also do, idlers. You can add more than 2 pulleys. So we'll come into this example. If I know that, for some reason, the way things for design criteria or spec that my pump and motor, they can't move, and they're at a set height, but the height is not good for any belt that I have, I can add a tensioner in. So we'll go back to the design accelerator, Synchronous-Belts. Again, we're going to select the belt mid plane here. Go to component, and it's going to be fixed by selected geometry. Come here and check, still 28 tooth. And then same thing with the next one. I'm going to go by fixed by selected geometry. .42, we're good there. And now what we're going to do is we're going to add a third pulley. So you can click here. And here's some of the different pulley options. If I had an existing pulley, I could choose that. A flat pulley. Then they also have the tooth pulleys that are flanged, unflanged, flanged on one side. For this, we're going to go with the double flange. And here we're going to select what we have in our system. And I have an 18 tooth off the shelf, so I'm going to use that. Now for the position, you can do a free sliding. Let me show you this. And it'll let you place it in that, if I don't have 114, but I have 120, I set the number of teeth to that. This is where this pulley needs to be at its tension spec for that belt to work. Or I can go to a rotation driven selection. So on my adjuster here, my hinge point, select there. Then I can still slide this up and down because it's still staying in that 114 tooth belt. And say that, there we go. You can change the rotation of what the pulleys are. If I know that, I'm going to be rotating it counterclockwise versus clockwise, you're able to do that. That's going to get me confused quickly. So we'll just go back in, set them up. And then after everything's set, you get the green, means that the belt is correct, that it has the tension built. So we go back to the calculations. After entering the information, calculate. Okay. So this will let you decide on where you need to put in tension if you need to, or tensioning the pulley without an idler. So if we can get rid of the visibility and do another one, I wanted to show you something. The component generator is going to remember the last set of inputs it did. So every time I clicked into the calculation, I already had 10 horsepower and the right RPMs. But if you come up here, there's the reset calculation data. Click that. It'll reset everything back to basics. So if I come into calculations, I need to enter it again. So again, selecting the plane, and it's going to be a component. It's going to be fixed by position. And here it starts off as a 25 because that's what the reset is. But I know that needs to be 28 because that's what fits the ratio, and that's what I have in or on hand in our parts. So we're not bringing in new parts to. So then we're going to also do the driven pulley here, fixed by selected geometry. We'll come up here, look at it. And here you can do it by a ratio. So I know it needs to be 0.8 and back. And it gives me a 42 pulley. And so we can see here that it's red because there's no tension in the belt or no way to tension it in the system that it sees. So if we add another pulley, it'll place it there and go to the calculations. It's telling me that the power that I'm trying to transfer will not work on a 3/4 belt. But if I go up to 1.5 inches, the calculation works. So I know before even actually trying it or running it that I need this width of a belt for the power transmission to work properly. Instead of trying it with smaller belt and going, oh, that didn't work, burn through all the teeth. No good. And you're able to add in pulleys and belts into the system by adjusting the XML file. You can get the data off, your pulley manufacturer, they will give you the data that you need to enter. So a summary of what we were going over was, the design accelerator, but primarily more for the power transmissions and synchronous belts. But in the design accelerator, there is tons of options for bolted connections, and if you input what the strengths of the connections need to be, it'll tell you which bolts, it'll tell you if it's going to be strong enough. Frame generator uses standard steel shapes and parts to generate your frames. So some very powerful and useful tools to not only speed up your designing or modeling, but also make sure it's correct and it's going to work and be strong enough to work. Nothing's worse than designing a project for a few months and actually building it and going, oh, that wasn't nearly the strength that frame member needed, the whole thing tweaked, and now back to the drawing board more or less. So any questions that we have so far?
Yep, and if you don't know how to answer or to ask a question, go ahead and type it into the questions panel. You should have that on your Zoom webinar, I guess, taskbar, I guess we'll call it. And then if you're on YouTube, go ahead and just type it in the comment section. I know that I monitor both. So let's go ahead and take a look at some of those. So we'll give everyone 30 seconds or so to ask any questions that you have. Before we jump into those questions, if you want to jump to the next slide too, Jeremy, let's go through this too. And here's some information about some of the projects that our team has been working on. I think Jeremy, you might be like heading a lot of these projects, just to, I guess, get to those cogs spinning in your brains as to things that you can solve by using some of the products you guys use on each and every day. So Jeremy, can you kind of describe some of those issues with the flat pattern creation that customer had and how
Yeah,
you know?
of course. Now, this came up a week or so ago, and as being in Lifeline, I get calls with issues, and the initial call was they wanted the flat pattern for the sheet metal to have no stretch taken out. It's like, okay, that's different, but okay. And so the solution was, change the K factor to 0, gave them the flat pattern. And then I asked, well, why don't you want, the stretch taken out of the part? Because that's, it's practical. And his answer was to make sure it fits on the nest. They were already starting with what the flat pattern size needed to be. Well, I was like, okay, I understand that. I grasp. And, I came from doing a lot of sheet metal and a lot of nesting and cost reduction ideas. And so just talking to him for a little bit, I was explaining some of the different methods that we used for, cutting the cost of the nesting down and saving on unused material and just the overall programming costs.
100%.
Yeah. And one of the things I was explaining to him, a way that we've done it before is instead of nesting each part on a nest, if you have a 4x8, sheet or a piece of sheet metal that you're going to cut out, and your part is, half of that or just over half, and you can only fit one. Well, that the way it nests and costs sometimes doesn't really reflect the true part. And so I was explaining that, if you roll all the parts into one nest and cost it as one part, because if they're all welded together, you can give them individual names, but when you cost it in your ERP and for nesting,
it's one thing.
Yeah. And I was asking him, like, do you ever plan on cutting out, 2 bracket A's, but only one base plate? He's like, no, it has to go together. I'm like, well, if you do it this way, it's not guaranteed, because there's no such thing as guaranteed in manufacturing, but it always tends to usually lend itself to keeping it more accurate 1-to-1. So we talked about that for a while, and yeah, it's just one of those ideas to help them, continue to get some cost reduction and just different ideas that, came from different industries.
Yep. And I know that a lot of organizations who have been working with sheet metal for a long time have been using the same kind of nesting software for the last 10, 15 years, right? It's something that you're familiar with. It's something that your machine shop has been using all the time. But something that a lot of people don't know is that with the product design and manufacturing collection, which I would say the vast majority of our Autodesk customers have, if you have AutoCAD and Inventor on your machine, odds are you have the full collection. It's just the most cost efficient way to get both. And that collection has like 15 products, one of which is like a nesting software within Inventor itself. So, things like file translation don't need to occur, and things like automatic updates to the nest and the parts within the nest, as opposed to like doing multiple DXF exports and all that fun stuff. Yeah, I've done like a couple of AVAs on that specifically. It's really cool when you can take a full-blown assembly with like 10 sheet metal parts and hit the nesting button, and it'll make the nest for all of the parts. It'll group all of the like thicknesses together, and then it'll give you all of your various sheets. So just something to keep in mind of too is like, as the products evolve, it might be worth it to take and explore as to what you currently have and how maybe you could use it in your workflows.
I completely agree. And I mean, you know, you may ask yourself, well, is it worth my time to look at something new? But nothing's worse than cutting out a part that, you know, you made changes on, but production didn't realize. So they cut out a
The
few
wrong one.
sheets of, yeah, and they're all scrap. And yeah.
Yeah, I can hear it in Jeremy's voice that may or may not have happened to him in the past.
Oh, it's happened a couple times in my life. Even after you tell them, you know, hey, there's changes, so, you know, hold off a second. Oh yeah, we just
like, oh, it's been burned already. Sorry. It's like,
okay,
oh,
guys.
okay. We're gonna have to toss that. So yeah. So I guess
Oh.
when we're going through all of this, you know, sheet metal aside, we got a couple of questions in regards to power transmission. So let's go ahead and go through those, Jeremy. The first one is from Ray, and Ray asks, does the Accelerator allow for a design that does not meet ISO standards? Will it let you put something that is not within standard?
Yes. Well, and on my first example here, that's why it gives me the warnings, but it'll let me override it. So,
and I think the same thing goes for like the V belts as well. If it gives you like a non-standard belt length, it'll just give you a warning.
Yeah, and what it'll end up doing is, you know, show you exactly. You know, and you can see right here that, yeah, since it's red, that's not in accordance to what ISO and the standards are going to be. And, you know, it's going to tell you roughly what the closest belt to it is, and that's not going to be accurate because you're not into the standards anymore. That'll be what the closest is to that length. And that's when you get these warnings that, you know, calculation failed.
Yep, the inputs are inconsistent with the in-build rules, which are the in-build rules are the ISO standards.
Yeah, but you're able to override it with, you know, accepting it, and you're able to do that.
Yep, so just keep that in mind too, is like, yeah, you can, it'll help you generate these pulley systems really fast, or these like power transmission systems really quickly. But you got to make sure that if you want it to meet a certain standard, or you want to be able to buy this belt off the shelf, read all of know what you're doing and read all of the dialog boxes.
Yeah.
All right. Another thing too from Ray, can the ISO power transmission, the ISO power transmission values be customized?
Ooh, that's a good question. I'll have to look into that one and get back. I'm not too sure if you can change the actual built-in rules per se.
I don't think you can.
Yeah, and
I think you can just override them so that like you get something like what you had just done, right?
Yeah. I'll look into that, see if you can actually change the ISO rules, but I would almost, you know, be hesitantly guessing that you couldn't, because if it's an ISO rule, probably wouldn't want you to, but I will.
Yeah, it's probably to the standard. Yeah, it's not like where you can make your own rule, like for example, for like sheet metal, because I guess that's just like pretty standard across the board. So yeah, it's for sure. Yeah, Ray mentions he's just curious about that. It's for sure a liability on the Autodesk end for sure. Yeah, if someone's allowed to build something incorrect and you order like 100,000 of these things and there's like they're all wrong.
Yeah.
Then you put 100,000 belts in the corner of your shop and you're like, yeah, these don't work. So
yep.
For sure. Okay, cool. I think that's just about everything for questions. I'll give everyone another 30 seconds or so to ask any. Jeremy, can you do me a favor and open a Chrome window and go to the KETIV website though?
One second.
Yep, and I'll let you drag that over when you're ready. Cool. Can you go into Academy for me and then to ANSYS Virtual Academy for me? Thank you so much. I just wanted to make a quick announcement too. is in addition to the Autodesk Virtual Academy, we have another AVA series called the ANSYS Virtual Academy that's hosted by my good friend JD here on the team. Kind of similar, except you go through ANSYS instead of Autodesk software. And the next ANSYS Virtual Academy session is actually in about a week and a half. I'm going over some thermal analysis for design engineering specifically. So I know that we have a lot of customers who traverse both the Autodesk and ANSYS space. So if you are an analyst, as well as like a designer for your company, and you're kind of a jack of all trades and you need to learn a little bit more about how thermal analysis will affect your systems and all of that, JD is going to be hosting a webinar going through that. A lot of the concepts can be used regardless of what simulation software you're using, right? Analysis is analysis. It just, the buttons and the way that it calculates and all of that might be different software to software, but I guess the concepts are kind of the same. So I just wanted to make that announcement. If you wanted to sign up, if you go to our website, go to Academy, we have the Fusion as well, and the ANSYS Virtual Academy in addition to this one. So if you're interested in any of those, go ahead and click through those and sign up, and you'll get emails similar to the ones you do for this version of AVA. So with that, I'd like to thank everybody for joining us today. Jeremy, I'd like to thank you for putting this all together. I know that there are a couple of more design accelerators that, we're probably going to work with you to get squared away. Let's, if anyone has any suggestions, you do get surveys after this. So if you can fill those out with any suggestions of future webinars you want to see, what you thought of today's session, that would be greatly appreciated. Any last words, Jeremy, before I let everybody go?
No, I think that's it. I just hope everybody has a great day.
Awesome. Yeah, everyone have a great day. If I don't talk to you before the weekend, you take it easy. So with that,
Oh, you too.
we'll bid you all adieu. Goodbye.
All right. Goodbye.